said this follows transform and conquer approach. So till now we were learning about greedy technique. So in a transform and conquer approach, what exactly it talks about is the design of your transform and conquer approach is a design method. Okay, it's based on transformation. The main idea is, as the name indicates, you're transforming and then you're conquering. So it has a two-stage procedure. One is called as transformation stage and the other stage is called as conquering stage. There are three different variations based on which you can transform. During the transformation stage, there are three ways in which you can transform. So accordingly, the way in which you solve the problem in the conquering stage will change. Okay, so the transformation can be based on instance simplification, meaning let's say you are having your uniqueness element. Okay, finding the unique element, we've already done this in your first unit. So when you're trying to find if there is any element which is not unique in a specific list of numbers, we saw that we had to take each number, check it with all the numbers in the list, and then proceed further. The other way in which we can do is instance simplification. In instance simplification, if you are taking the say n numbers, we needed to check each number with every other number in the list to find if the number is repeating or not. Okay, the other way in which we can do it by using transform, that is brute force method. Fine. Now in transform and conquer stage, what we can do is we can first apply the best sorting technique and sort all the elements in a row. So if you take merge sort takes only n log n, even in the worst case. So if we are let's say using merge sort, the time complexity will be only n log n. Otherwise it basically goes up to n square. So if you are taking n log and if you are sorting, then all you need to do is after sorting, you start checking with the first element with the next element. If in case there are two numbers which are same, then both the elements will be same. So in that case, halfway through, we can stop checking and we can come out. So this is instance simplification. We are transforming the input into a method wherein the resultant that we get is a simplified form of solving. The second one is representation change. That is, you're changing from one representation to another representation. Let's say if you use Gaussian method, okay, there's a method called as Gaussian method, which basically has a very big equation which needs to be solved. Now, this particular equation can be transformed into a set of linear equations. So you're changing the entire representation from a big one equation into smaller set of n number of equations. So then you use linear algebra to solve those linear equations, and then finally you get the answer. The third one is problem reduction. When you're talking about problem reduction, this is similar to your divide and conquer approach, wherein you're going to reduce the problem into small instance and then you're going to solve it. Okay. So coming to your heap and heap sort, if you take the name heap, the heap basically indicates that everything is put one on top of the other, nothing is ordered. Correct? So here what we are going to do is, in computer, in data structure terminology, heap is not something that is unordered. Fine. So we will be looking at it. And for doing this heap, the one main important thing which we need to know is priority queues. Okay. So what's a priority queue? A priority queue is a multi-set of items with an orderable characteristic. Okay, that is called priority. So you're having a set of items, each and every item having one priority value. And this particular priority value has the following operations. First thing, you find the minimum or the maximum. So you're basically finding an element with highest priority. After you find the element with the highest priority, whether it's a minimum value or a maximum value, then you delete the item with the highest priority. And after you delete the item with the highest priority, you'll insert a new item into the multiset. So this is one way in which you can talk about priority queue, how it works. Now, heap basically uses all these three operations. That is, finding item with highest priority, deleting an item with the highest priority, adding new item into the multi-set. So it all uses all these three operations, and that is what makes it very interesting and useful. And that is how this heap basically becomes the cornerstone of your sorting problem with sorting technique, which is called as heap sort. So we're going to learn about heaps, and we're going to learn how to create a heap. Then we're going to learn how to use it in a heap sort algorithm. Fine. So when you're talking about heap, what's a heap? The definition of a heap. In English, we tell heap is just stacking everything one above the other. Whereas when you're talking about the heap over here, it is defined as a binary tree, okay, with keys assigned to the nodes, one key per node, provided two conditions are met. First is tree shape requirement, and the second one is parental dominance requirement. So heap is a binary tree with which has values, and these values should basically satisfy two requirements. One is tree shape requirement, the other one is parental dominance requirement. When you're talking about tree shape requirement, that means it should be a complete binary tree. What's a complete binary tree? Nobody's answering. So when you're talking about a complete binary tree, basically it's a tree which has okay, all the child nodes. You have a parent node, and that parent node should have all the child nodes for each level. Only the condition here is for in a heap, the last level of your binary tree need not have all the child nodes. But from the left side only, it should start including the nodes into the tree. Fine. So this is your tree shape requirement. The second one is parental dominance requirement. In parental dominance requirement, it means the keys of each node should be greater than or equal to its children nodes. Okay. Key is given at each and every node. Now supposing say here if I'm telling this is 7, this is 6, and this is 5, then it is fine. The parent node is always greater than the child node. Okay. So that is how it has to happen. So heap, you can also call it as a clever partially ordered data structure useful for implementing priority queues. Fine. So let's take examples. Now you guys are going to answer me. Fine. If you know the answer, you can also raise your hand. So identify if a given tree is a heap or not. Is this a heap or not? You can message.
Yes, ma'am.
Yes, ma'am.
This is a heap. Okay. How about, then you're right. Then how about this?
Yeah, that's also a heap, ma'am.
Ma'am. Oh, yes.
Also a heap?
Yes,
Yes,
ma'am.
yes, ma'am.
Heap basically has two requirements, right? What are the two requirements? Yeah, it should be a
Except the
complete
last
binary
node.
tree except the last level, wherein I said it should start from the leftmost node only. Here, is it starting from the leftmost node? This left child is missing. So this cannot be
Yes.
a complete binary tree. With okay, so tree shape requirement is not satisfied. So this is not a heap. Okay, I'll give you another graph. Let's say if you can tell me. Yeah, this one.
No.
Why
No,
not?
it's not.
Yes,
Because
ma'am,
6
it
is
is.
greater than 5.
6 is greater than 5. So parental dominance requirement is not met, and hence it is also not a heap. So you need to learn to observe carefully of the values that is given to tell if it is a heap or not. Okay. So that being said, there are different properties for a heap. We need to understand the properties of a heap as well. So what's the first property of a heap? The first property of a heap is there exists only one complete binary tree with n nodes. Okay, there always exists exactly one complete binary tree with n nodes, with its height always equal to log n to the base 2, because we know it should always be 2 power n nodes. Okay, in a binary tree. Now, the second property is the root of the heap is always the largest element, the topmost root. Okay, the first node should always be the largest element, because every other node that follows, parental dominance should be present. Okay, then the node of heap taken together with all its descendants basically is also a heap. So when you are taking the root node, then the child node also will become a heap, right? The left subtree. Okay, if you are having a tree, if you remove the root node, you have the left subtree and the right subtree. Again, the left subtree, the root node has to be the greatest element, correct? So if we are taking the a node of a heap along with all its descendants, even that should be a heap. So heap implementation, how do we implement a heap? Okay, once we have a heap as in the form of a tree, there are different ways you can represent a heap. So what we are going to do is, before we create a heap, we'll always get the elements in the form of an array. Yes, so we need to always get the elements in the form of an array. So the first representation that we can use is an array representation. Let's just see how this array representation works. If you are taking this, yeah, now this is the tree that I am taking, which is a heap. If I want to convert this heap into an array representation, I have to start doing from top to bottom, left to right. Top to bottom, left to right, I need to take the elements and I need to start placing it one above the other. So now first element is 9. So I'm going to place it over here. Then the next element, which is 5. Okay, left to right. So 5 gets placed over here. 7 gets put over here. Then I come to 4, put it here. 2 comes here. And 1 comes here. So it is left to right, top to bottom. So now if you see this particular figure, we can try to analyze few things from this particular representation. The topmost or the root element is the very first element in the array. And the root of the left subtree is the second element. The root of the right subtree is the third element. So if you take this particular value, now this is 1, 2, 3, 4, 5, 6, right? So fourth position, whatever value we have, that is the leftmost child of the left subtree. Okay, so if I divide this 4 by 2, okay, if I divide this by 2, I basically get the value 2. So that will be the root of my node. Now if you take 5, again 5 is divided by 2. So 5 by 2 gives you 2.5. And 2.5, if I take the integer part, it is only 2. So again it is right child of 5. So right child will be the next element and the left child will be the value of n divided by 2, wherein j divided by 2, wherein j is the positional value of that particular node. And if you take the last value in the array, will be the last node that is present. Okay, so we can always start from here, find the root of that particular node, and then we can go for the previous one, which will be the left side subtree of that particular node. So this again will be a root. So like that we can go till the root to do the heapify. Okay, so we'll see. Whatever I told you, I'll just show it to you now. Left child of any node at a position j. Like now if I take j equal to 4, j equal to 2. The left child of 5 is in the position 4, that is 2 into 2. So the right child will be in 2 into 2 plus 1. Okay, so that is the thing we need to remember. Okay, it exists in the next one if in case there exists a right child. Now here there is no right child, so 6 plus 1 7, there is no position over there. And parent of j, you can always tell it is present in j divided by 2. Okay, so 2 divided by 2 is 1, so parent of 5 is in the first position. And we are starting from 1 till n and not from 0, so that we don't get confused with the positions when we are doing heap and heap sort. Okay, so parental nodes, you should know, are in the first n by 2 positions of the array. So if the total array is 6, the array size here is 6, 6 by 2 is 3. So all the parental positions are in the first half, and the last half will contain all the child nodes. Okay, so this is how a heap is represented in the form of an array. We need to understand this so that we know how to proceed further. Store heap elements in positions through 1 to n. Element, the 0th position will be used unused, or it can be used as sentinel. So these things we've learned. Now let's see how to construct a heap. So given a set of elements, we should know how to construct a heap. So first is initializing heap structure with keys in order. Then we start with the last parental node. So if you divide the total size by 2, we get the last parental node. So we will start with that. And then we will fix the heap rooted at it. If it fails heap condition, then exchange the larger child with the root node. We will see how this works, and we repeat this process till the heap condition is completely satisfied. Now once this step is over, then you repeat the previous step for preceding parental node. So we do that for all the nodes. Now let's consider these values: 2, 9, 1, 6, 5, 7. So this is the set of values which we have. Okay, we have to put it into an array. So construct the heap in order. So first put it into an array. Now once we put it into an array, we need to know the positions of these values. So it is 1, 2, 3, 4, 5, 6. So 6 divided by 2 is 3. So this will be the root node, the rightmost root node. I mean parental nodes. This will be the last parental node, and from then we have to go on, because we know parent should always be a greater value. Okay, so let us heapify. In order to heapify, the first thing that we will do is, what's the last parental node? 6 by 2 is 3. Position 3. In position 3 we have 1, and we find that 1 is always smaller. 1 is smaller than 7. So since the parent should always be a value which is greater, we are going to exchange 1 and 7. So when you exchange 1 and 7, we will exchange these two values. So it becomes 2, 9, 7, 6, 5 and 1. So this basically becomes this way. We're going to exchange these two values. We're going to get 7 there and 1 here. Now this basically satisfies the heapify condition over here. Okay. Again we need to go for the previous node.
Can you please explain this step one more time?
Okay, I'll just repeat. The first thing is, we had all the numbers, we've put it in the array. Once I put it in the array, what I'm doing is I'm taking the last parental node. Last parental node we know is in n by 2th position. Okay, n is the total number of nodes. Here total number of nodes, if you take, this is 1, 2, 3, 4, 5, 6. So there are totally 6 values. And among these 6 values, the last parental node will be 6 by 2, which is third position. So this basically is the last parental node. So if you see 2, 9 and 1, these are the last parental nodes. These 3 are the child nodes. Now this last parental node, I need to verify if it is greater than my child node. Now here if you find 1 is less than 7, it is not greater. So this is not in the form of a heap. So I need to first convert this into the form of a heap. So that is why I will exchange 1 and 7. And when I exchange 1 and 7, this is what I finally get. So I get 2, 9, 7, 6, 5 and 1. Now that step 1 is over. The step 2 is doing the same thing for the remaining parental nodes. Okay, so next I need to check for the previous node. Previous hop node, if I see, it is 9. 9 is greater than 7, so I don't have to break my head. It is still in heap format. Now I go to the next parental node, which is 2. Okay, 9 is greater than 6. 9 is also greater than 5. So this is in heap. This left side tree is in the form of a heap. I don't have to break my head. So I need to again go check with the previous value, which is the root node for these two nodes. So when I check 2, I find 2 is less than 9. So I will be exchanging 2 and 9. So when I exchange 2 and 9, I basically get 9 on top, 2 over here. So this is the next step. We will see how it follows. Okay, so here if you see, 7 and 1 has been exchanged. So heap property satisfies. Now once we have this, next step I told you is checking for 9. Okay, so when I'm checking for 9, 9 is at position 2, and I find that both these nodes are less than 9, so I don't have to break my head. No exchange is required. Next parental node is 2, which is at the first position. This needs heapification because 2 is less than 9, 2 is also less than 7. So we'll take the greatest among these child nodes and we will put it in the place of 2. So what you're getting, we will be exchanging 2 and 9. So when you exchange 2 and 9, basically you get. Now if I see the left side subtree is not exactly in the form of a heap. So then I need to check with the child nodes. I have 2, so I need to exchange 6 and all over again. Okay, so node 2 is not in order. It needs to be exchanged. If 9 is greater than 6 and 7, true. 6 is greater than 5, 2. 7 is greater than 1, 2. So parent dominance requirement is satisfied and shape requirement is also satisfied. So we can basically consider this as a heap. You understood how to create a heap given a set of numbers. So coming to heap algorithm, there are two ways in which you can construct heap. One is bottom-up approach and the approach. We are following the bottom-up approach. So in bottom-up approach, we are doing for I equals n to 1. That is, we are starting from the leftmost parent, the last parent node. From there till this node, what we are doing is we are making k equal to e and we are putting head of k as the vertex. And heap we are making it false. Then we are checking it's not a heap. Okay. Heap will be false if it's not a heap. And there are 2 into k. So here, if I is n by 2, okay, say 3. 3 into 2 is 6. So we go for the 6th position and we start checking from there. Okay, because we need to check the right node and then the left node as well. Okay, so j we are making it as 2 into k. It will give me the left child of my parental node. Okay, left child of my parental node, I take it as j and check if it's less than n. That means if there are 2 children. If it's equal, that means there's only one child. Okay, like here. For 7, this will be only one child, so that means it will be equal to n. Otherwise, it will be less than n. So this is to check if there are 2 children. If there are 2 children, I need to check for the rightmost child as well. Okay, so I check if h of j, which is this value, is less than h of j plus 1. So if this is less than this, then I need to go to this particular position. If not, I can remain over here itself. Okay, so if j is less than n and this condition is false, directly I'll check if that value is greater than v the vertex. Okay, this node. I'm checking if this is greater than this. If it is true, then I'll basically make heap as true because we already know that this is greater than this and this is also greater than this. We'll send heap as true. So again, when it comes and checks here, it finds it is heap. So it comes out of this while loop and then increments I. Okay, so decrements I. So I goes to the previous parent. Now again, you're doing the same thing. I'm making the heap as false because every time I will consider the heap, it is not a heap before I can prove that that particular subtree is a heap. You understand? So I'll be first starting from the last parental node, checking if it is not, I'm making sure that it is not a heap. Then I'm going to check with both the left child and the right child. Check if which of the child is the smallest one. If this is whichever is smaller, I'm sorry, if h of this is the greater one. So I'm going to find out which is the number. I'll stick to a particular node and then I check if the value is also greater than the vertex. And greater than the vertex, then I can basically make my heap as I can tell heap is not an exchange. If not, if vertex greater than that particular child node, then it is heap. If vertex is not greater than child, then I will exchange h of n, and I will proceed further.